So we will be studying chemical thermodynamics. We will not only be talking about delta H, which is the enthalpy of a reaction, or the heat in our case. We will be also talking about delta S, which is entropy. And combining these two will give us delta G, which is free energy. Okay. First, let's discuss the laws of thermodynamics. The first one is that energy is conserved. So if you put energy into a light bulb, all that energy that you put in must add up to what comes out, light and heat. Okay, this equals to this. The second law of thermodynamics talks about entropy. So entropy talks about the degree of randomness and the degree of disorder in a system. So this is low entropy because it's very ordered. As you melt it, it becomes higher in entropy. Okay. The third law of thermodynamics says that at 0 Kelvin, the entropy is equal to 0. Okay. So here, if the molecules are not moving at all, then it has the lowest entropy possible. As you increase the temperature, the entropy will only go up. So entropy goes from 0 and it goes higher. They are not negative. Okay. So entropy talks about spontaneous process. Okay. So if you open this valve, those molecules or atoms will spontaneously go to the other side. They will not spontaneously go back. So that's non-spontaneous. Spontaneous also happens at a certain temperature. So let's say we are melting ice. Okay, if you're above 0 degrees Celsius, it will melt spontaneously. But if you're below 0 degrees Celsius, then it will not be spontaneous. It will be non-spontaneous. So processes that are spontaneous at one temperature may not be spontaneous at another. Okay, so we're also going to talk about reversible processes. Of course, reversible means you can put it back. It's easier to talk about irreversible. Here's an irreversible process. You have a gas in here. You open this little partition and the gas expands. So that is irreversible because the gas won't go back on the other side by itself. You have to put work in. Okay, that's why it's not reversible, so it's irreversible. And spontaneous processes are irreversible because to make it go back, you have to do work. Okay, so let's look at 19.1 and we're going to predict whether something is spontaneous. As described, spontaneous in the reverse direction or at equilibrium. So for example, when a piece of metal is heated to 150 degrees, is added to water, so you have a hot metal and you're putting it into water, the water gets hot. Of course, that is spontaneous because when you put this in, the energy will go from the metal to the water spontaneously. Water at room temperature decomposes into, so if you have water, it will break apart into H2 and O2. That will not happen. You have to put energy into there to break the bonds of the H and the O. Okay, so that is not spontaneous in that way, but it is spontaneous going backwards. Okay, it says benzene vapor C6H6 at a pressure of 1 atm condenses to liquid. So you're starting from gas and you're going to liquid. So that's condensation, and that's happening at the boiling point. Okay, so if this is the boiling point, this is the temperature by which the liquid goes into a gas. Okay, you're warming it up. Because at that temperature, you're at equilibrium because the liquid will go up to gas and the gas will go down to a liquid. You are at equilibrium. Okay, so this system is at equilibrium. Okay, so what is entropy? Entropy can be thought of as a measure of randomness. Okay, it is related to various modes of motion. So you have to, later on we'll be talking about how these molecules are moving. Okay, and it is also a state function. So let's look at this graph so I can describe to you what I mean by state function. So here you have at 0 Kelvin down here, the molecules are not moving or the atoms are not moving at all. That's 0 entropy. S is a symbol for entropy. As you melt it, the entropy goes up. Okay, as you increase the temperature, it turns into a liquid and turns to a gas. So the entropy just goes higher and higher and higher. Remember, it goes from 0 to a higher number. Okay, so there's no such thing as negative S. But the delta S could be different. So the delta S is the change from final to initial. So if you're here, if let's say this number is 10 and this is 5, and you're going from gas to liquid, so 10 final minus initial, 10 minus 5 is equal to positive 5. So the change is positive going into gas. But of course, if you're going down to liquid, it's not, it's becoming more ordered, then you're going to do liquid, which is 5, minus 10, you're going to get negative delta S. And that is not spontaneous because it's not spontaneous from gas to go to liquid. It would rather turn into gas. Okay? So again, here delta S is always final minus initial. So entropy, this is coined by Rudolf Clausius. He's a German physicist. And it is actually a number. It is a ratio of heat delivered at a certain temperature. So it's Q over T. So Q stands for heat at a certain temperature. Okay. So the symbol for the entropy is delta S, change in entropy. It's heat over the temperature, and the unit for heat is J, and it is unit for temperature is always going to be Kelvin. Okay, so since delta S is a state function, that means it doesn't matter how you get there, but the gap between these two is always a certain number. It is a state function. So even though it's reversible, irreversible, doesn't really matter, you're going to get the same number. Okay, so let's go ahead and calculate the delta S for a phase change. You're melting ice. You have 1 mole of it. You're adding heat from the surroundings. So heat is equal to delta H, is equal to heat plus work. We're not doing any work here. We're just putting heat into the system. So here, in case the work will be 0, so Q equals delta H. So here, so delta S equals Q over T. Q is equal to delta H of fusion, which is 6.01 kilojoules per mole. That number is given. That's how much energy you need to heat up or to melt ice, 1 mole of ice. Kilojoules for every 1 mole. And you're doing this at 273 K. Okay, so we're going to go ahead and multiply this by 1 mole to get the J over K. So we have the moles will cancel, multiply the kJs will cancel, and your unit will be J over K. So delta S is in units of J over K. It's the amount of heat you put in at a certain temperature. Okay, so let's go ahead and calculate this. Okay, so the element mercury, Hg, is silver. Silvery liquid at room temperature. The normal freezing point is negative 38.9 degrees Celsius. Its molar enthalpy of fusion is 2.29 kilojoules per mole. What is the entropy change? So they're looking for delta S when 50 grams of mercury freezes at normal freezing point. Okay, so the formula is that what you're going to be using is